Good morning, everyone. Welcome to our internship presentation. Today, we are excited to share our work on the Smart Factory IoT monitoring system. My name is Swaram S., and along with my colleagues Sanjay S. and Vikash R., we have developed this project to enhance factory efficiency through IoT technology. Over the next few minutes, we'll walk you through the key features, the implementation process, and the potential impact of our system. Thank you for being here, and let's get started. Now, let's look at some of the key features of our smart factory concept. First, it connects automation, IoT, and cloud analytics seamlessly. This integration allows us to gather and analyze data across the entire industrial environment in real time. By doing so, we can monitor operations instantly and respond quickly to any issues. This setup really boosts efficiency, safety, and helps us make smarter decisions faster. We built this model using Arduino simulation with PixSimLab and connected everything to the ThingsBoard cloud platform. Overall, this approach exemplifies how modern technology can transform traditional factories into smarter, more responsive environments. Let's start by looking at how we can monitor dynamic factory conditions in real time. This means having the ability to see what's happening on the factory floor instantly, which is crucial for maintaining safety and efficiency. Next, automating critical responses is key. Think of situations like emergency ventilation that needs to kick in immediately to protect workers and equipment. Automating these responses helps us react faster and more reliably than manual interventions. Another important aspect is facilitating remote control through a centralized cloud dashboard. This allows us to oversee and manage operations from anywhere, providing flexibility and better oversight across multiple locations. Detecting equipment faults early is also vital. By catching issues before they become major problems, we can trigger immediate alarms, minimizing downtime and preventing costly damages. Finally, all these capabilities come together in developing a highly scalable, industry-ready architecture. This ensures that our system can grow with our needs and integrate seamlessly into existing industrial environments. These objectives tie directly into our overall goal, creating a smarter, safer, and more efficient factory environment through advanced technology. Now, let's take a closer look at how the system is structured. It's divided into two main functional nodes, the production line node and the warehouse node. These nodes work together to manage different parts of the operation efficiently. What's really important here is that the system supports bidirectional communication. This means we have an uplink, where sensor data from the production line and warehouse is sent to the cloud, and then displayed on a dashboard for easy monitoring. On the other side, we have the downlink, which allows commands from the dashboard to be sent back to the edge devices. This setup enables us to not only monitor in real time, but also control the system remotely and automate processes locally. Overall, this integration provides a comprehensive overview, combining real-time monitoring with remote control capabilities, making the system both flexible and responsive to operational needs. Let's take a closer look at the system architecture. This slide illustrates how all the different components of our system come together to form a cohesive and efficient framework. First, you'll notice the core modules, which are responsible for the main functions we need to perform. These modules communicate with each other through well-defined interfaces, ensuring smooth data flow and coordination. It's important to highlight that the architecture is designed with scalability in mind, so we can easily add new features or handle increased load over time. Additionally, security layers are integrated throughout the system, protecting our data and maintaining integrity. Connecting this to the overall theme of the presentation, a solid architecture is the backbone that supports reliability, performance, and future growth. Understanding how these pieces fit together helps us appreciate the robustness of the solution we're building. Today, I'll walk you through the hardware components we're using in this system. First, the microcontroller at the heart of everything is the Arduino Uno, which serves as the main processing unit. It's reliable, easy to program, and perfect for our application. For ambient tracking, we're utilizing the DHT22 sensor, which measures temperature and humidity levels, and the LDR, or light-dependent resistor, to monitor light intensity. These sensors help us keep an eye on environmental conditions in real time. When it comes to machine monitoring, we've included the LM35 temperature sensor. It specifically tracks the temperature of machinery, enabling us to detect overheating issues early. For security and safety, we've integrated a peer sensor, which detects motion. This adds a layer of security by alerting us to any unexpected movement in the monitored area. Finally, for actuation, we're using relay modules and indicator LEDs. The relays allow us to control various devices and equipment remotely or automatically, while the LEDs provide visual status indicators. It's worth noting that we've physically mapped and verified all these components using Pixim Lab simulation, ensuring everything works seamlessly together in our system. This comprehensive setup forms the backbone of our environmental monitoring, safety, and automation solution. In this slide, I want to highlight our primary focus, which is maintaining equipment health and monitoring operational status. To do this, we've implemented continuous polling of the LM35 temperature sensors on our machines. This allows us to keep real-time tabs on temperature fluctuations that could indicate potential issues. Additionally, we've integrated vibration anomaly detection, which is crucial for catching early signs of mechanical problems before they lead to costly breakdowns. Monitoring the machine's power state, whether it's on or off, helps us ensure the equipment is operating as expected and assists in troubleshooting. We've also added relay control for emergency shutdowns, giving us the ability to quickly cut power in critical situations, enhancing safety and preventing damage. All this data is transmitted every 5 seconds, providing a steady stream of information to our monitoring system. Specifically, for Node 1, which is our production line, these measures work together to keep the machinery running smoothly, minimize downtime, and support overall operational efficiency. This continuous monitoring and control are vital parts of our strategy to ensure reliable manufacturing processes. Now, let's take a closer look at the primary focus of this slide, which is the inventory environment and security. We're monitoring key parameters to ensure optimal storage conditions and safety. First, ambient temperature and humidity are tracked continuously, because maintaining the right environment is crucial for inventory quality. If humidity rises to 85%, for example, our system automatically triggers the exhaust fans via relay to prevent damage. We also keep an eye on motion using peer sensors and lighting levels with LDRs. These not only help in managing energy consumption by ensuring lights are on only when needed, but also improve security by detecting unauthorized movement. Another important aspect is door status tracking, so we always know when doors are opened or closed, adding an extra layer of security and control. All these functions are integrated into our edge logic, which executes automatically. For instance, if humidity hits that critical 85% mark, the system responds immediately to activate exhaust fans, no manual intervention needed. In essence, this setup creates a smart, responsive environment that safeguards inventory while optimizing energy and security management in our warehouse. This slide highlights some of the key reasons why MQTT is a great choice for our communication needs. First, it's chosen for its lightweight footprint, meaning it doesn't require much bandwidth or resources, which is especially important for IoT devices that often have limited capabilities. This efficiency helps keep the system fast and responsive. Next, MQTT's publish-subscribe architecture plays a crucial role in preventing system blocking. Instead of devices waiting for responses, they simply publish or subscribe to topics, allowing for asynchronous communication. This makes the overall system more resilient and scalable. We also see that there are 2 main message types in MQTT. The first is telemetry data, which refers to sensor readings sent to the cloud for analysis or storage. The second is RPC commands, or remote procedure calls, which are instructions sent to devices to perform specific actions. Finally, the communication protocol itself is MQTT. Its design perfectly aligns with our goals of efficiency, scalability, and real-time data exchange. All these features combined make MQTT an ideal protocol for our IoT ecosystem. Now, let's take a closer look at how we built our system using standard modular programming practices. First, we have the sensor manager, which is responsible for handling raw data acquisition. This component makes sure that all sensor inputs are collected efficiently and accurately. Next, there's the actuator manager, which controls relays and LEDs, enabling us to manage physical outputs seamlessly. Then, we have the network manager, which maintains the MQTT connection. This is essential for reliable communication between our device and the cloud. Moving on, the telemetry manager takes care of packaging and formatting JSON payloads, ensuring data is structured properly for transmission and analysis. Lastly, the RPC handler is crucial as it parses incoming commands from the cloud, allowing for remote control and configuration. By designing our software this way, we're not only making it easier to manage and troubleshoot, but we're also aligning with best practices for modular development. This approach enhances flexibility, scalability, and maintainability, key factors for a robust IoT system. Connecting all these components, we create a cohesive, efficient architecture that supports the overall goals of our project. Now, let's take a closer look at the cloud dashboard interface. At the core, we have a centralized UI built on Things board, which serves as the main control and visualization platform. This setup allows us to monitor and manage all the sensor data from a single, intuitive interface. One of the key features is the real-time digital gauges, which display live sensor values. This means we can see immediate updates on parameters like temperature and humidity, helping us respond quickly to any changes. In addition, we have time series graphs that track trends over time for temperature and humidity. These graphs are vital for analyzing patterns and understanding how environmental conditions fluctuate, enabling better decision-making. The interface also includes interactive control widgets, such as remote on and off switches. These give us the ability to remotely control devices or systems directly from the dashboard, adding a layer of convenience and operational efficiency. Finally, there are visual alarm indicators integrated into the interface. These alerts immediately notify us of any abnormal conditions, ensuring that issues are promptly addressed and system reliability is maintained. Altogether, this dashboard provides a comprehensive, real-time view of our environmental data, combined with control capabilities, making it a powerful tool for managing our system effectively. Now, let's look at how our system makes smart edge decisions. What this means is that it doesn't have to wait for the cloud to respond before acting on critical parameters. Instead, it can process data locally and make immediate decisions. For example, autoventilation can kick in right away based on humidity thresholds, ensuring quick response times and improved comfort. Moving on to remote overrides. This feature allows managers to intervene directly through the dashboard using remote procedure calls, or RPC. So, if necessary, they can override local automation to adapt quickly to changing conditions or special circumstances. Finally, we have the status LEDs. These provide a clear, physical confirmation of digital commands being executed. It's a simple yet effective way to verify that the system is responding correctly, bridging the digital and physical aspects of control. All these features work together to enhance our automation capabilities, making the system both smarter and more flexible, aligning seamlessly with our overall goal of creating an intelligent, responsive environment. All right, let's talk about the programmed thresholds we've set up. First, if the temperature exceeds 35 degrees Celsius, the system will trigger a critical alarm and send a notification to the dashboard. This helps us respond quickly to potential overheating issues. Next, if humidity levels go above 85%, the system activates the ventilation to help regulate the environment and logs a warning event for future review. And finally, if we experience missing data or a sensor drop, the system will trigger a system failure warning, indicating that something might be wrong with the sensors or the data flow. The overall goal here is to aim for zero downtime and to prevent any thermal damage that could occur due to these conditions. These alarm and safety protocols are essential because they allow us to act swiftly and maintain the safety and integrity of the system. They're all about proactive management, making sure we catch issues early before they escalate into bigger problems. This ties into the broader theme of keeping our operations safe, reliable, and efficient at all times. Now, let's look at the results of our system testing and validation. First, test case 1 involved real-time telemetry upload, which is crucial for maintaining up-to-date system data. I'm pleased to report that this test passed, confirming our system's ability to transmit data accurately and promptly. Next, test case 2 focused on motion detection and security alerts. This is key for ensuring safety and security, and again, it passed, indicating our detection algorithms and alert mechanisms are functioning reliably. Moving on to test case 3, which tested the autonomous ventilation trigger. This feature is essential for optimizing environmental conditions automatically, and it also passed, demonstrating our system can effectively manage ventilation without manual intervention. Lastly, test case 4 tested network stability, specifically network drop scenarios and MQTT auto-reconnect functionality. This aspect is vital for maintaining consistent communication, especially in unpredictable network conditions. I'm happy to report that this test passed as well. Overall, these successful tests reinforce that our system is robust, reliable, and ready for deployment, aligning perfectly with our goal of creating a resilient and autonomous solution. Now, let's explore the practical architecture of end-to-end IoT systems. Here, we focus on how all the components, from sensors to cloud services, integrate seamlessly to create a reliable and scalable solution. Understanding this architecture is fundamental to designing effective IoT deployments. Next, we'll delve into the implementation of MQTT in embedded environments. MQTT is a lightweight messaging protocol that's ideal for resource-constrained devices, enabling efficient and real-time data exchange. Mastering its deployment ensures smooth communication across your IoT ecosystem. We'll also cover troubleshooting physical and simulated sensor interfacing. Sensors can sometimes be tricky, whether due to hardware issues, wiring, or software bugs, so developing strong troubleshooting skills is crucial for maintaining system integrity and performance. Moving on, we'll discuss how to structure cloud data and design user experiences for dashboards. Organizing data effectively in the cloud allows for quick analysis, while intuitive dashboards make insights accessible and actionable for users. Finally, we'll see how to translate Industry 4 concepts into working prototypes. This involves taking the latest industrial innovations, like automation, data analytics, and interconnected systems, and turning them into tangible, functional prototypes that demonstrate their practical value. All these points tie back to our overall goal, equipping you with the key skills and knowledge to develop robust, innovative IoT solutions that are ready for real-world applications. Now, let's look at some real-world applications of Industry 4 technologies. First, we have smart factory floors, which are central to the Industry 4 transition. These smart factories leverage IoT sensors, automation, and data analytics to optimize production processes, increase flexibility, and improve quality. It's all about creating more intelligent and adaptable manufacturing environments. Next, we see cold chain and warehouse monitoring. This involves using sensors and IoT devices to ensure proper storage conditions, track temperatures in real time, and prevent spoilage or damage during transportation and storage. It's crucial for industries like food, pharmaceuticals, and chemicals, where maintaining the right conditions is vital. Then we have predictive maintenance pipelines. Instead of waiting for machines to break down, we now monitor equipment continuously to predict failures before they happen. This proactive approach reduces downtime, cuts costs, and extends machinery lifespan, making maintenance smarter and more efficient. Finally, automated occupational safety systems are becoming more common. These systems use sensors, AI, and automation to monitor workplace safety conditions, detect hazards, and alert workers or management instantly. This helps create safer work environments and reduces accidents. All these examples demonstrate how Industry 4 is transforming industries in practical, impactful ways, making operations more efficient, safer, and more responsive to real-time data. Now, looking ahead, we're planning to integrate support vector machine models to enhance our predictive maintenance capabilities. This shift from simple threshold logic to more advanced machine learning models will give us better accuracy and early fault detection. We're also moving from the simulation environment into deploying our system on a custom-designed physical PCB, which means more real-world testing and reliability. To ensure easy access and control, we'll develop a dedicated mobile app that communicates via REST APIs, making the system more user-friendly. Additionally, we'll implement deep sleep modes on our devices to optimize energy consumption, extending battery life and reducing maintenance needs. These improvements are all about making our system smarter, more robust, and ready for real-world application. So, we've successfully built and validated a complete end-to-end IoT monitoring loop. This means we now have a system that can continuously collect data, analyze it, and respond in real time. It's a significant step forward in ensuring more efficient and reliable operations. We've also effectively combined passive data monitoring with active automated control. This integration allows us to not only observe what's happening, but also to automatically make adjustments when needed, which improves responsiveness and reduces manual intervention. The architecture we've developed is scalable and cost-effective, meaning it can grow with your needs without breaking the bank. Plus, it's ready for further industrial integration, opening doors to more advanced applications and broader deployment. Overall, this approach aligns perfectly with our goal of creating smarter, more autonomous industrial systems that can adapt and optimize themselves over time. Questions and feedback. I'd love to hear your thoughts or any questions you might have. Thank you so much for your time and attention today. Your input is really valuable as we look to improve and grow. Please feel free to share any comments or ask anything that's on your mind. Thanks again for being part of this presentation.
So basically, this is a node 1, which is production line. This is LM35. This is DHT22 sensor where we have temperature and humidity. Here we have temperature. Now this is vibration sensor. For vibration sensor, we have used a potentiometer. For machine control, we have used a button. This is for relay status. And now this is our three LEDs. If the system is proper, then green light will be on. If there is any error in connection, like connection is wrong, then this yellow LED will be blink. And if there is most this error, then this light will be glow up. Now let's talk about warehouse. In warehouse, we have DHT22 sensor. Here we measuring temperature and humidity. This is PIR sensor. For PIR sensor, we have used the switches. Because of this, we can detect any motion is there or not. We have used LDR sensor for light. This is door switch. Is door is on or off. This is ventilation relay. If the humidity is greater than certain limit, this ventilation relay will be green. And all this stuff. Now let's talk about things. Let's talk about things about cloud. Let's check our all three dashboards. So this is production line monitor. This is production line. Basically, this is production line monitor node 1. Here we can see clearly temperature level is 36, humidity is 48. So let's check in production line. If I'm right, yes, production line. Let's check in for production line. This is production line. Now we change the temperature of LM35, all this, and now check. Sorry, I have done mistake. Okay, let's check. Here we have seeing that there is change in temperature. Now machine status is on, relay status is on, and sensor error, there is no sensor error. And here is we getting the data printed. Here we have used alarms. This is high temperature alarm. Severity is critical. If the temperature is some line above, then it will show critical. Now let's talk about second dashboard, which is warehouse monitoring. Warehouse monitor, which is node 2. So let's change the temperature, humidity, all that stuff. LDR, okay. So here temperature is minus 25, 65. LDR value is 2. They go. Okay, now this has been changed as temperature is very high, 40 degree. Humidity is in between that. This is fluctuating as I change the values. So this is door status, this is dark or not, this is motion detected, this is sensor error, and here we have seen the time series charge of humidity. Humidity is fluctuating with time. This is time series table, and these are the alarms which we have created. Now let's check, is there a will be ventilation is working or not properly. So if humidity is greater than 85 or 90, relay should be on. So this is working properly. So here, so let's change humidity. So we can see here, as I change the humidity, there is dip in the humidity. Here humidity is 64. Now we have changed its value. We have changed LDR value. We have changed temperature value. Now we can check it. So all this is our node 2. We can see all these changes. As I change my humidity value, it has been changed. As I change my temperature value, it has been changed, and LDR value is also changed. Now we talk about smart factory. This is the combination of both the warehouse and production line monitors. This is warehouse node 1 data, this is node 2 data, and this is time series charge for it, chart for it. Okay, all these, and these are the two devices, warehouse and production line.